So this is a joint work with Professor Nadir Rashid, Professor Raoul Tamponi, and Professor Mohammed Salim Albani. And let's start by the problem setting. Suppose that we have a process X evolving over time and that we have the SDE for X. Suppose that we want to know how much time the signal X stays below a given threshold. So if you see here in this picture, we have the signal X is in blue. When the signal falls below a given threshold, here gamma is 0.5, we call this fade, and we introduce a new random process, z of t, which is the sum of these fade durations up to time t. And our quantity of interest will be z at capital time t, which is the sum of the fade duration in the whole interval 0t. And our goal in this work is to determine the distribution of z at capital time t. There are many applications for this, and in particular, I will be interested in wireless communication systems. So we will use this for the performance analysis of such systems. And let's give some notation for this application. So the signal psi can be represented as a combination of the in-phase I and quadrature Q. So the in-phase is the real part of the signal and the quadrature is the imaginary part of the signal. In the literature, I and Q are modeled by Markovian uncorrelated Gaussian random processes with time-varying means and variances. So they can be written as the solution of the following Eulenberg SDE. And our signal will be our received signal will be the square root of I square plus Q square. And depending on the distribution of X can be Rayleigh, Rice, Hoyt, or in general Beckman distribution. And the fade duration in this application is how much time the signal envelope stays below a given threshold gamma. In this talk, I will cover these sections. First, I will propose a Monte Carlo estimator for the estimation of the complementary CDF of the fade duration. Then I will motivate the need for importance sampling for the right tail of the CCDF. Then we will see that having an optimal change of measure for the importance sampling needs the solving a high dimensional PDE. That's why we need to reduce the dimensionality of our SDE, and we will use for this Markovian projection. And finally, I will give numerical results for the estimation of the CCDF with importance sampling estimators. Let's start by the Monte Carlo estimator and see how this problem can be formulated with estimating Monte Carlo estimator. So Z is the fade time, so it can be written as the solution of the following ODE. Then we embed the SDE for I and Q with the ODE for Z to obtain a three-dimensional SDE. The complementary CDF of Z is written as the probability that Z at capital time t is greater than W, and then we vary W from 0 to t to obtain the figure of the CCDF. This probability can be written as the expectation of the indicator function of Z greater than W. Then if we solve the previous SDE, we will have M samples of Z, and the Monte Carlo estimator is the mean average of GW of this independent samples. Here is an example of estimating the complementary CDF in the Rayleigh case. Rayleigh case meaning that I and Q have asymptotically zero mean and same variance. So this is an example for some parameters of the CCDF. As you see, it's a decreasing function towards zero. And in the tail, we can observe that we have very small values. So the Monte Carlo estimator, for example, for the blue curve, estimates 0 for W greater than 3.5. But we know that it's a very rare event, estimating the probability that Z of t is greater than W, which is approaching the tail, approaching capital time t. So we know that it's very small value, and Monte Carlo estimator needs a large number of samples to estimate this probability accurately. That's why I will introduce in this section importance sampling, which is a tool for reducing the variance and then reducing the number of samples to compute the tail of the complementary CDF. So here again is the motivation. So in terms of relative error, the relative error of the Monte Carlo estimator can be written in this setting as inversely proportional to m times the quantity of interest, the probability. So if we fix the relative error, in order to obtain an accurate estimates, we need a large number of samples. And here I plot the relative error as a function of W. And as you see here, as we approach to the tail, the relative error is huge. And importance sampling will allow us to reduce this relative error. I will give the idea of importance sampling in general and then move to the SDE setting. So in general, if we have random vector X with PDF F, and we want to estimate the expectation of some function G of X, the idea is to write this expectation in the integral form, multiply and divide by a new density called F tilde, and then we will have this expectation is exactly the same expectation of G tilde of X, but X now is sampled according to F tilde, and G tilde is G times the likelihood, which is F over F tilde. F tilde is chosen in such a way we increase the occurrence of the rare event. And the importance sampling estimator is finally the mean average of G tilde of X, but now X are sampled from F tilde and not from F. In the SDE setting, if we have X solving a given SDE and we want to estimate the expectation of G of X at final time t given initial condition, the importance sampling or the change of measure in the importance sampling is performed in the path space induced by the Wiener process. So using Guernazov theorem, we can show that the new path X zeta solves a controlled SDE with an additional term here compared to the original SDE we have in the drift. There is an additional term which is the diffusion times the control. And the control is chosen to minimize the variance of our estimator. So similar to the previous slide, we have an unbiased estimator with multiplying by likelihood. So this expectation of our quantity of interest will be the expectation of G of the controlled process times the likelihood. And the likelihood can be defined as follows. As we said, the control will be chosen to minimize the variance. We have unbiased estimator, so minimizing the variance is equivalent to minimizing the second moment. That's why the cost function will be the second moment of our estimator. We also define the value function, which is the minimum over all the possible controls of the cost function. And therefore, we can formulate the problem of finding an optimal change of measure as a stochastic optimal control problem. And from control theory, we can use this interesting result, which tells us that the value function, if it's bounded and smooth, then it solves the following PDE. And the optimal control is given by 1/2 the diffusion of our SDE times the gradient of log of the solution of this PDE. Suppose that G does not change the sign, and we propose a change of variable U square equal V. Then if we plug into here, we will find that U solves the Kolmogorov backward equation given by this PDE. And we know that the solution of the KBE corresponds to exactly to the expectation of G of X at final time t. So we have U square equal to V. Then the square of the expectation is equal to V, which is the second moment. V is the value function, which is the minimum of the second moment. So we have expectation square equal to the second moment. Then our optimal change of measure produce a zero variance estimator. Interesting remark is that solving the Kolmogorov backward equation suffers from curse of dimensionality, because the dimensionality of our PDE is the same as the dimensionality of the problem. So if we return to our application where we have I, Q, and Z, to find an optimal change of measure, we will need 1 dimension in time and 3 dimensions in space, which is computationally expensive. One solution to this is to derive an SDE for the square envelope of I square and Q square, and we will use a tool called Markovian projection, and then we will apply the change of measure to the SDE for R and Z instead of I, Q, and Z. And with this, we will reduce the dimensionality of our PDE from 3 dimensions in space to 2 dimensions in space. And that's why I will now introduce the Markovian projection, and we will see how we will use it to find a reduced SDE for the square envelope. So we will use this lemma, which says that if we have a process X, which is d-dimensional, and solve the following SDE, if we want to find an SDE for the projection of P times X, but if S is non-Markovian, which is our case, because starting from I and Q to find an SDE for I square plus Q square using the I2 formula, we will find that R is not Markovian. So which is the case here in the state of the lemma. The lemma says that we can find a process S bar that mimics this non-Markovian process S, which is a projection of X, and the dimension of S is D bar, which is less than D. And we can find the drift and diffusion of this of the SDE of this projected process S bar. The drift and diffusions are given by the following formulas, and the lemma tells us that S and S bar have the same conditional distribution. Let's see how we'll use it in our problem. So here I choose the Rayleigh case. I and Q solve the following SDE, and we want to find an SDE for I square plus Q square. As I said, if we use I2 formula, this is the SDE that we have, which is non-Markovian. But we need Markovian SDE, that's why we will use Markovian projection. So applying the lemma with taking X equal IQR, our quantity of interest is R, which is a projection of X. And we let R bar to be the Markovian projection of R. And from the Markovian projection lemma, it solves the following SDE with the following drift and diffusion. Here, computing the drift and diffusion is easy, and we have exact expressions. And from the lemma, we know that R bar and R have the same condition distribution given initial condition. So here is the SDE for R bar now. And in order to check its distribution, we plot here I square, the histogram of I square plus Q square by solving the SDE for I and Q, and the histogram of R bar by solving the following SDE, and we see that we have the same distribution. Now I will move to more complicated case, which is the Rice case. Now asymptotically, the mean of I and Q is not 0 anymore. We have theta as mean. And again, the SDE for R is non-Markovian, and we will use Markovian projection to find a Markovian SDE with drift A bar and diffusion B bar. So this is the expression of A bar and B bar. But the problem here is that it's not easy to compute this conditional expectation, because we need to calculate the conditional expectation of Q given R and I given R. That's why we need to compute the conditional PDF of I given R. And if we assume that I and Q are the same, so it will be the same for Q. And here we have some expressions. So here is the final expression of the conditional PDF of I given R. And finally, the conditional expectation in the drift is computed as the integral of X times this PDF. So we don't have an explicit expression of this integral. And if we plug it into the SDE as it is, it will be expensive to solve it numerically for each time step and for each sample. That's why we'll try to approximate this to find an expression of this conditional expectation. We will use affine prediction. So we'll suppose that this expectation is equal to this expression, to this affine expression. And given that I is Gaussian and R is exponential, we can easily find the expressions of these constants, these functions C1 and C2. And here I plot the drift. So in the drift, we have this conditional expectation. I can compute the integral here numerically, and I plot the exact drift in blue. And I also plot the drift if I approximate the conditional expectation using affine prediction. And here we can see a good match between both, and then we can use the affine prediction to estimate the SDE for R bar in the Rice case. This is the final expression of an approximated SDE. And here is the histogram of I square plus Q square and R bar. And here we have there is this mismatch because of the approximation in the drift. The final case is the Hoyt case, when theta 1 and theta 2, the asymptotic mean of I and Q are 0, but I and Q have different variance. And this is the difference between this and the Rayleigh case. Again, the same steps. We use Markovian projection to find an SDE for R bar, which is the square envelope. Here is the expressions of A bar and B bar. Again, we need to compute some conditional expectation, but now it's I square given R, not I given R. And again, we assume that I and Q are the same, with assuming that they start from the same point, and we can express the conditional PDF of I square given R in this way, and the conditional expectation of I square given R is the integral again, but in this case we were lucky to find an explicit expression of this integral via computations, and we can do the same for Q by replacing sigma 1 by sigma 2 and sigma 2 by sigma 1. And here is the histogram. As we found an explicit expression of the conditional expectation, and then we can find the exact drift for the projected SDE, we have a good match between the histogram of I square plus Q square and R bar. Now, let's summarize what we have seen. So we proposed an importance sampling estimator to deal with the right tail of the importance sampling. But we saw that an optimal change of measure will need solving a PDE with the dimension of the problem. That's why we used Markovian projection to reduce the dimensionality of our original SDE. So now, instead of applying a change of measure on I and Q, we will apply it on R, and then we will have computational feasibility of solving the PDE to find an optimal change of measure. And let's start by the Rayleigh case, where we have found the exact SDE for R bar. So I will use the theorem that I presented before for the optimal change of measure. So the controlled process, now R bar, zeta, and Z bar, will solve the following controlled SDE. So we have this additional term here in the drift, which is diffusion times the control. And in order to find an optimal control, we will use the control theory, and we will use the result that the optimal control is the diffusion times the derivative of x of log of the solution of this PDE. This PDE is exactly the Kolmogorov backward equation corresponding to this SDE, the original SDE for R. And let's see how importance sampling will affect the trajectories of X and Z. So here let's focus on the first figure, 4.1, which is for W equal 2. So we will try to estimate the probability that Z of t is greater than 2, which is of the order of 10 to the power minus 2. In the left, we have this plots of the paths for X, the solution of the original SDE. So X is I squared plus Q squared, or the square root of I squared plus Q squared. And then in green, we will have the controlled process, X zeta, by solving the controlled SDE. And in the right, we have the same for the paths of Z and Z zeta. So if you see for X, after applying the change of measure, the control will push the paths to be below the threshold, 0.5. And the fading time for the green processes will be larger than the blue paths, and therefore we are pushing the paths toward the rare event. And we see this here for the paths of Z. So originally, these are the paths of Z at final time t. Only 2 samples are greater than 2. But we want to increase this occurrence, and after applying the change of measure, the control will push this paths in order to have Z at capital time t greater than 2. And here we see more samples that are greater than 2. Here I plot only 20 samples, but absolutely in our work we use more samples. Now in the second figure, what is changing is how rare the event is. So we increase W. By increasing W, we are making the event more rare. So now the probability of Z at capital time t greater than 3 is of the order of 10 to the power minus 4. So in the first figure here for X, we see that the control is pushing X more to be below the threshold. And we can see this more clearly for Z. So now we want Z at capital time t to be greater than 3 and not only greater than 2. And we see here the sharp change in the paths of Z. And we have few samples now that are greater than 3, while for the original 20 samples that I plotted for Z, no sample is greater than 3. And with this, we see that the control will push the paths to be below the threshold, and therefore we will increase the occurrence of the rare event, and therefore the importance sampling will allow us to estimate the probability in the tail with high accuracy. And here is the final result. In the left, I plot the estimated complementary CDF using Monte Carlo and importance sampling to see that our estimator is unbiased. And in the right, I plot the relative error. And as you see, there is a gain in terms of relative error for importance sampling compared to the naive Monte Carlo. Also in this figure, I plot the number of samples needed for a fixed relative error. So I fix it to 5%. And as you see here, for Monte Carlo, it needs a huge number of samples, especially in the tail, but importance sampling succeed to reduce this number of samples and make the computation of this probability feasible. These are also some values. So here the values of W, as you see, for W greater than 3.5, the Monte Carlo estimator estimates 0. But the importance sampling can estimate these very small values of the order of 10 to the power minus 7, minus 9, minus 11, and with good variance. This is also the variance of estimating these very small values, it's also very small. And we can also see the reduction of variance for the values here for 2.5 until 3.25. There is variance reduction compared to Monte Carlo. Now I will move to the second case, which is Rice. And what is different in this case is that if you remember, when we used the Markovian projection, we did not find an exact drift for the projected SDE. We used affine prediction, and we had an approximated drift A tilde instead of A bar. So if we will use this drift and do the same as we did for the Rayleigh case, we will introduce some bias when we estimate the expectation of G of Z bar relative to the original quantity of interest. That's why we will not apply the change of measure to the reduced SDE, but we will apply to the original SDE for I and Q. And now the controlled SDE, after applying the change of measure to I, Q, and Z, is the following. So now we have two controls, one for I and one for Q. And if we use the control theory to find an optimal control for this full dimension SDE, these are the expressions of our optimal controls. So it's the diffusion times the gradient of log of V, and V here is the solution of the Kolmogorov-Backward equation associated with the full dimension SDE. So V is the solution of three-dimension PDE. So it's computationally expensive, and that's why it's not possible in this case to find an optimal control for I and Q. But instead, we can use the same theory, but on the full dimension SDE. So we will propose suboptimal controls by using the optimal controls for the reduced SDE, and then mapping the optimal controls for the reduced SDE to the suboptimal controls for the full dimensional SDE. In other words, we will approximate this value function for the high dimensional SDE by this lower dimensional value function. And VL now is the solution of the KBE of the projected SDE. So we can find the solution of such KBE. And we now have the expression of VL. And finally, the suboptimal controls, zeta1 and zeta2, will be written as follows. So we approximate the derivative here, the derivative of the log of VH by this expression here. And let's see if we will get variance reduction or not. And the answer is yes. Here we plot the estimated tail for the complementary CDF using Monte Carlo and importance sampling. As we see here, we have an unbiased estimator. And in terms of number of samples needed for a fixed relative error, we see obviously the reduction in the number of samples. So let's now move to the conclusion. What we saw here in the talk is introducing the fading duration, which is the time during which the channel remains in fade. We employed Monte Carlo estimator to estimate the complementary CDF, and then we motivated the need of importance sampling for efficiently estimating the right tail of the CCDF of the fade duration. Then we proposed an optimal change of measure for the importance sampling, and we highlighted that we necessitate reduced dimensional SDE. That's why we introduced Markovian projection, which is a tool that allows us to move from two-dimensional SDE into one-dimensional SDE. We investigated 3 cases. Rayleigh, Rice, and Hoyt, we gave the expressions of the projected SDE for these cases. And then we presented some numerical results for the CCDF of the fade duration in the Rayleigh and Rice cases. And we showed how important sampling significantly reduced the number of simulation runs for a fixed relative error. These are some references, and this is our paper in archive, and it's under review in IEEE journal if you want further details. And thank you for your attention.